Artificial intelligence is shifting from simply responding to questions to independently navigating tasks. These systems analyze a goal, perceive their digital environment, and execute the necessary tools to reach a conclusion without human prompting. To understand this shift, look at this diagram comparing two distinct workflows. On the left, you see traditional AI. It is strictly linear. You feed it a prompt, it generates a response, and it stops. Now look at the right side. This represents an agentic system. Instead of a one-way street, the agent loops through perception, memory, and tool use. It has the discretion to decide if it needs to pull more data or trigger another tool before it delivers the final output. Giving an AI this level of freedom requires two distinct frameworks. You need a reasoning pattern, which dictates how the agent thinks through a problem, and a design pattern, which structures how the entire system is organized. Granting a system the authority to loop through its own decisions makes it an active collaborator, but without a strict structural framework, that same autonomy can lead to infinite loops or unpredictable modifications to your production environment. So, as a developer, you face a major architectural choice. Do you build one highly capable agent packed with instructions, or do you wire together a network of smaller, specialized agents? Load a single agent with too many responsibilities and you hit a hard ceiling. The context window fills up, the model loses track of which tool to call, and you get severe, unpredictable hallucinations. But splitting the work comes with its own risks. This diagram shows what happens when a multi-agent system breaks down. Agents get stuck in infinite loops, endlessly passing messages back and forth while racking up massive API token costs without ever finishing the task. Every added layer introduces new latency, higher token costs, and more points of failure. Because of these concrete trade-offs, the most robust system is the one that applies the absolute minimum level of agency required to solve the problem. To prevent an agent from blindly guessing, you rely on a reasoning pattern. Think of this as the internal cognitive rhythm that externalizes the AI's logic into visible steps. The foundation of this logic is mapped out here in this diagram of the React pattern. It forces the model through three distinct steps. It generates an internal thought about the objective, executes an action by calling a tool, and processes the resulting observation. Because it processes real-world feedback, the agent can actively adjust its strategy mid-task if the initial plan isn't working. That adaptability has a price. Because the model must call itself multiple times to complete a single objective, token consumption and latency spike significantly compared to a standard prompt. But by forcing the model to write out its internal logic step by step, developers can pinpoint the exact moment reasoning breaks down. You are deliberately trading speed to gain dynamic problem-solving and full auditability. Sometimes straightforward linear logic falls short. When a task requires deep strategic foresight, an agent needs a way to test multiple hypotheses at once. This structural approach is known as the tree of thoughts, shown here. The model generates multiple potential solutions simultaneously. If one path hits a dead end, it backtracks and focuses its computational power on the remaining viable branches. You can stack this with reflection, a self-correction loop where a secondary evaluator node pauses to review the output, critiques it for errors, and sends it back through the tree for refinement before the user ever sees it. The computational overhead here is massive. Running a tree of thoughts with a reflection loop will effectively double or even triple the wait time for a final answer. These deep cognition patterns push hallucinations to near zero. But unless you are dealing with complex math or intricate legal analysis, spending this much compute is overkill for standard business workflows. Once you decide how the agent thinks, you have to decide how it lives in your infrastructure. Design patterns are the architectural blueprints that turn that raw reasoning into a governable, secure system. The baseline structure is a single agent architecture. You equip one core language model with a dedicated memory buffer and a specific suite of tools. Because there is only one entity making decisions, its execution path remains highly predictable. If a tool fails or a loop breaks, you only have one context window to debug. You can expand its capabilities using Anthropic's routing pattern, shown in this diagram. Instead of overwhelming the model with every tool at once, a classifier looks at the incoming query and cleanly diverts the data to an isolated, highly specialized subprompt. For most enterprise applications, this single agent design provides the perfect balance of dynamic logic and strict control. However, if your workflow demands expertise across multiple unrelated domains simultaneously, a single agent will inevitably drop the ball. When a task spans several disconnected departments, you need a multi-agent hierarchical system. This allows you to distribute complexity across separate specialized models. Here is how that architecture functions. A top-level supervisor agent evaluates the overarching goal, breaks a large task down into operational pieces, and delegates those pieces to specialized worker swarms below it. In this setup, a shared centralized memory is required. Without a single source of truth to anchor them, individual agents will start making decisions based on conflicting, outdated versions of the project state. The primary point of failure here is the orchestrator bottleneck. If the supervisor becomes overwhelmed trying to coordinate dozens of workers, tracing a logic error back to a specific agent becomes nearly impossible. Multi-agent systems bypass the limitations of a single context window, but by layering agents on top of agents, you exponentially multiply your infrastructure costs and your potential points of failure. This flowchart outlines exactly how to map your project to the correct architecture. It all starts with one question: what is your primary constraint? If your priority is low latency, low cost, and handling iterative tasks like customer support workflows, you build a single agent architecture utilizing standard React and routing patterns. It keeps token usage down and execution fast. If you are building for a data scientist where accuracy is critical, like financial modeling, and processing time is flexible, you stick to a single agent setup, forcing the model through the computational lifting of tree of thoughts and reflection loops. Finally, if you're an enterprise architect designing a global order system integrating tax compliance, shipping, and legal review simultaneously, you deploy a multi-agent hierarchy. Ensure it's governed by centralized memory and clear checkpoints for human review. The rule for agent development is strict restraint. Do not upgrade your system's complexity until the cognitive limits of your current pattern are fully exhausted. The reasoning patterns will determine how deeply your agent thinks about a problem, while the design patterns dictate how safely those thoughts are executed in the real world. Building a reliable automated worker depends on engineering the specific level of architectural control needed to ground and stabilize raw model intelligence.